Hello, I'm Paul Swenson. I'm a master's student at SMU's Masters of Data Science program, and we're going to talk about some stock data today. So, real quick, I just want to give an introduction to exactly the data that we're looking at. These entries have 7,744 records and contains open, high, low, and close data for a stock. So here you can see the open, high, low, and close. And this data is collected minute by minute over the course of a couple of weeks. This is just a quick summary of the data. And what we're trying to do with this data is we're trying to predict the close price of the stock in the following minutes. Given all the data, uh, if we're able to predict if the stock price increases or decreases, then that would let us be able to buy or sell stocks in a way that we can guarantee that we can make money, assuming the model performs well. So I've defined two separate time bands here, 5 minutes for short term and 60 minutes for long term predictions. And on the plot to the right, if you think of the red data point as the predicted and the black data point as the actual, if we were trying to predict the next stock price and we see that it increases, then we might be able to use that as a form of investment. This is an overview of what the close price looks like for the entirety of our data set. You can see there's a really strong wandering behavior. It doesn't seem to follow any kind of seasonal patterns or anything like that, at least on the first glance. Here we have the autocorrelation plots, frequency periodogram, and the Parson window. On the bottom right plot, there are a whole bunch of tiny little frequencies that may occur here, but overall it doesn't seem like there's any that really stand out. The ACF plot in the top right also kind of follows our hypothesis that this data follows just a wandering behavior. There's no real correlation between any of the ACFs. So what I wanted to do first was just create a really basic model. So if we assumed that the stock price was going to stay exactly the same as the previous observation, then we would just essentially predict that the next price is going to be the same as the current price. So this is what the baseline model would look like. And overall, for 60 predicted observations, we had an ASE of about 0.8. So that'll be a good reference when measuring the success of the following models that we're going to get into right now. The first one we have, I wanted to filter it to see if there was any way that we could isolate the white noise. And just by running a couple of different functions in R, I was able to pull out that the optimal AIC occurs with P equal to 1 and Q equal to 2 for an ARMA model. Um, Now, I was able to remove a 1 minus b component, and you'll see that in the top right plots here. So after removing the 1 minus b component, the transformed realization here in this bottom left plot looks just like white noise. So accounting for that, we can create the model with a 1 minus b component and then a p value of 1 and a q value of 2, and the resultant model is what's shown here at the bottom right. These are some of the stats with the ARMA 1-2 model with a 1 minus b component, and the 5-minute ASE is 2.66, so this is significantly higher than what we were seeing in our baseline model before. Remember, the baseline model was 0.8. So this model doesn't look very good, and overall, it kind of just predicts the same values over the course of the entire forecast for both 60-minute and 5-minute. Next, I wanted to use a VAR model using the open, high, low, and close values. So with this model, we have an ASE of 1.29, which is lower than our previous model that we just looked at. But again, still ASE is going to be significantly worse than the baseline model that we're kind of using to evaluate this against. So VAR model, even with open, high, low, and close features added in, is still not very successful. I also ran an MLP model, univariate, so this was only using the close price. And this one was performing significantly worse than even the VAR model. So I don't think that this one is really valuable to look at overall. I also created an ensemble MLP model, and funny enough, this one performed even worse than the previous MLP model, at least by the ASE standards when forecasting. I also created a multivariate ensemble model, so we have a whole bunch of models all predicting at the same time, and we just take the average prediction using these. And with this ensemble model, we saw a lot better performance than the previous ensemble model, but still not even as good as the VAR model, and definitely not as good as our baseline model. This is a summary of all the models. You'll see overall the best ASE was with the baseline model of zero point 0.8. So this kind of goes to show, even though we have all these really cool and useful machine learning modeling techniques, not all of them are going to give us exactly what we need. And in the case of stock data, I don't think that it is easy to predict the next observations. Otherwise, everyone would be using these models and modeling techniques to predict stock data, and we'd all be millionaires. So that's all I have. Thank you for listening.